Okay, I think we're ready. So today we're going to go a little bit more with type theory, and then we're going to talk about invisible math. And then next time we're going to start doing lean proper. So to maybe first let us review what we did the last time. Quick review. So we considered type theory as a formalism. We said it's just describing sets, okay? As a first iteration, you can just imagine it's sets. Its scope is much wider, but let's not worry about that. And you can imagine that it's a strange way of describing sets. And what's strange about it is that we didn't start with logic, but instead we said we're just going to directly describe basic constructions. And so we said there are going to be types, which you can think of as sets. These types have elements. And the only kind of thing we can say after that, after having ways of constructing elements and types, is to postulate some equations. So these were our basic ingredients, and I was drawing an analogy with how algebra works, where we have operations and equations, right? So if you look at something like a ring, it's just operations and equations. So in that sense, it's similar, but it's also more involved and more expressive. In fact, it's so expressive that you can do mathematics in it. So then we had some basic constructions. And I think we looked at binary products and sums. And then we did dependent products, so families of types. Our types can be dependent, which means that a type may depend on an element. Examples are everywhere, all over math, and we talked about that. Then we had the dependent sum. There were special cases, right? So function space was also turned out to be a special case of a product where you have a non-dependent family, so you get a function space. I think this is about how far we got, but then we also discussed logic, and we said, okay, so what do we do with logic if we eliminated Utra? We eliminated logic. We said, well, we're going to do logic via types, and the idea was that logical statements correspond to types with at most one element. So we had subsingletons. This was still kind of also maybe a little bit informal, the idea that we have subsingletons. And the idea was that if you have a type, you say that it's true. Okay, so informally you think of this as meaning has an element. The reason we started with subsingletons was that, a statement is true and it can't be true in 7 different ways. So let's use subsingletons because those are types that have at most one element. So if it has an element, it's unique. So then that's like a unique way of being true. And if it's empty, then it's not true, it's false. But we quickly realized that actually we maybe don't have to use subsingletons, that in some cases there will be different ways of a statement being true. So let's review how we had a little table of how this works. And so why did we use subsingletons? The reason we used subsingletons is because then we could just reuse these other constructions as logical connectives. So how did that work? So we had this table, which goes under the name Curry-Howard correspondence. And if this were France, we would make a big deal out of it. So conjunction turns out, so conjunction of two statements turns out to be just Cartesian product, and my tablet is, I don't know, is it dying or what's it doing? So this turns out to be precisely just Cartesian product, because if you use Cartesian product, you will see that it's got exactly the right rules to follow this idea that to have an element is to be true and to not have an element is to be false, because a Cartesian product has an element if and only if both elements, both A and B, have an element. Okay, so then we had implication. Implication turns out to be just function space. Then we had disjunction, and disjunction was kind of interesting because if you just use the sum of two types, then this is what we would call maybe an explicit disjunction, or this would actually be a decision procedure, right? You explicitly decide whether A holds or B holds when you give an element, because there will be possibly two ways in which A plus B can have an element. It can have an element in A, or it can have an element in B. So now it's not a sub-singleton in general. And we said, is this a problem? Well, it's a problem if we think that elements have to, that logical statements can only be true in one way, but this is kind of useful, so maybe we deviate from that. But if we don't, if we insist on one way, then we would truncate, right? So we said we would truncate. So there are various notations for this, various ways of doing this, but the idea is you smash the type together, right? So you have a type, and then you quotient it by the trivial equivalence relation. So if you quotient the empty type by the trivial equivalence relation, you'll get the empty type. But if you quotient some other type that has an element, if it has 17 elements, then you're just going to get a type that has a single equivalence class with 7 elements in it. So it's going to be a singleton. So this is like an artificial way of turning things into singletons. It's not that artificial because it has a universal property, and it's important to be aware of it. So this is now what I would call disjunction. And this one then follows the rules. So the rules of logic correspond to this one. But I want to keep this one in mind. Then we had for all x in A, say P of x. This turns out to be precisely a product. Then we had exists. And here again, we were in a similar situation as with the disjunction. So you could say that this corresponds to the dependent sum. Oh, yeah, so I might not be writing these pi's. Usually when you write a pi, you write the indexing like down here, and then you have a smaller font. So also in lean and in like when you don't have, it makes sense to write like this. So I might switch to this. Okay, so this again, when you make a sum, you get a type that can possibly have more than one element. So you say it's not a singleton. Should we worry about this? What's going on? Well, we could always truncate. So just smash it all together. Right? And if you look at the rules for an existential existential quantifier, it's really this correspondence that gives you what you want. So this is existential. But this is like an explicit construction. So what's the difference? Here you prove that something exists, and whatever your proof was, you forget what it is that you found, right? Because why? Because this, if there is an x in A satisfying P of x, then this type will be a singleton. So as evidence, you will offer the equivalence class that's the only element. So you will give the entire set of all the possible witnesses without actually choosing one. It's like, here's your whole set. I'm not telling you which one I want. So that's why it's going to be, it's correctly it's correctly capturing the idea that we proved that something exists, but we did not specify what it is that exists. We just passed over the set of all things that exist. And so, okay. Whereas here, remember what the elements of this type were. The elements were explicitly pairs. So to give evidence to have an element in this type means to have a pair where the first component is an element of A and the second component is a proof that it satisfies the property P, but that's not an existential. That's an explicit construction of an element satisfying a certain condition. So it's better to call it a construction. And I argued last time that if you just use first order logic, then you are only reduced to these smash things. So you cannot really speak about constructions in a meaningful way. You can just build terms in the term language or your first order logic, but that's usually too simple. It's too simplistic. Involved mathematical constructions are combinations of many steps involving logic and constructions. So as you're constructing an involved mathematical structure, element of some structure, such as a manifold or a smooth manifold, you need to maybe prove theorems on the way to constructing your thing, the thing of interest. So it's all going to be mixed up. So this idea of first order logic, that we have a simple algebra of terms, and then on top of that we have logical statements, is not actually sufficient for capturing mathematical practice the way it's actually done. There is a translation, right? Something like first order logic plus set theory, you can translate, but you have to be always like, you modify all your arguments so that they really are statements in first order logic and so on. You can do that, but for formalization, we don't want to do that because as humans, we don't want to do that. We want to just keep doing what we're doing. So it's actually good that we will have all of this. There is another side to this coin, which is if you take original type theory of Martin Löf, then you're not going to have this smashing business. If you don't have the smashing business, then you're reduced to the other extreme. You can never have a disjunction. You always have to make a decision, and you can never have an existential statement. You always have to make a construction. And so that is also a problem, because now there will be certain things you can't express. For instance, there is no reasonable way to express surjectivity of a function this way. Because as soon as you say that a function is surjective, you will actually explain how to construct a section, a right inverse of it, and that's too strong. Surjection is not the same thing as having a right inverse. So that's also not satisfactory. There's a nice paper by Martin Escardo where he shows that Brouwer's statement, all functions are continuous, if you express it using Martin Löf type theory without smashing, it's false, which is very ironic because Martin Löf type theory was designed to capture constructive mathematics. Brouwer's continuity statement, all functions are continuous, is kind of, that it doesn't get more constructive than that you claim that all functions are continuous. And that one you cannot even express now in Martin Löf type theory. So there should be a good middle ground, and I claim the good middle ground is that you need to have both of these because both of these are relevant to mathematical practice. Okay, so that's what we had last time. But now if you look at this, there's one important bit missing, which is equality, right? So we said, okay, we have equations, sure, okay, but at the level of logic, we would like to have equations here. And the kind of equations we had last time, they were like inference rules. So we still want equations as types, right? So we want equality. So the question is, how about equality as type? Can we do that, right? And that's something that we should discuss, because even though we have equations up here, we had these equations that said things like the first projection of a pair A, B is A, and so on. Those are kind of very rigid, and they're also a little bit at the wrong level. We want them at the same level as the rest of logic, which means we need to express them as types. Okay, so how would we do that? Okay, so the thing that we want is called identity type. Now we're out of review. We're now doing new things. And that's a new kind of construction where we want to say, okay, how do we make, so let's make a naive attempt. We want to have a type which is a subsingleton, which has an element if and only if two elements are equal. So suppose we have two elements x and y. Does this do anything? Why does this keep? Okay, so this doesn't do anything. This, okay, I give up. And then the AI in this tablet and software is not very advanced. Okay, so the idea would be like this. We want to have a type. Let's call it id. Okay, and suppose A is a type. So let's first see what we have. Suppose A is a type, and we have two elements. Let's call them x and y in A. And so now we would want something like this. Id A x, y. So this is a dependent type because it depends both on x and y. Okay, so what should this be? So naively, I will just say, okay, it should be the empty type. Presumably we can have the empty. I'm just going to write it as an empty set. So if x is not y, and it has to have an element, and I'm going to call this element right now, I'll just call it raffle for reasons that will become clear later, if x equals y. Well, let's be a little bit more precise about this element. So we would want to have a singleton, and if we're really pedantic, we would say something like raffle A of x, just to keep all the information alive, if x equals y, like this. And I'm going to do this. You can do this in your notebook as well. Okay, there we go. So, okay, that's the idea. Because, I mean, I'm just following this idea. I want to have a type, which is a subsingleton, and if it has an element, then it's true, and if it doesn't have an element, it's false. Yes? So this is what this is. It's doing precisely that. This is a fine idea, but this is not how you give inference rules in type theory. I mean, what is this? Curly brackets, here's some sort of case distinction, where this come from. This is using informal mathematics. We have to be a little bit more formal. So how do you do this formally? Okay, so formally what you do is, so you look at this, okay, so we're not actually going to actively say that it must be empty when x and y are not equal, because we don't have any good way of saying not equal until we actually have the identity type. So there's not you cannot have x not equal. There are only equations. There are no negated equations anywhere. So what we do instead is we give conditions under which we have this element. And then if those conditions are not satisfied, well, then we don't have this element, right? So there will still be a question of, okay, but how do you know it's equal? How do you know it's empty when they're actually different? But that's something that we'll discuss later. So the idea is you just say, okay, we're going to have a type. So let's remember how we give type theoretic rules. So the first one is you explain that there is a new type, new constructor that makes types. Let's see if I could hit the right length of the line. So you say, okay, so we discussed that there are these dashes and stuff. So the last time. So actually, I'm not going to call them x and y now, because then people might think they're variables, but they're really actually terms, meta variables. Okay, so okay, I don't want to get into that. So if you have A in A and you have B in A, then you can form a type, and it will call it id A B, and it's a type. So right at this moment, we don't know what the elements are, other than, yep, there's a construction called identity type. So now we have to say under what circumstances this happens, okay? And the rule goes like this. You say, if I have an element A in A, then there's an element called refl A of A, which is an element of id A, A, A. Okay, that's what I want to say. There must also be, we follow the pattern, right? So now I know how to make elements. So the only element I can make is refl, which is capturing this idea up here. And now I will have to have ways of using the element, right? So how? So this is a constructor. So there is also an eliminator or a deconstructor. Okay, it is traditionally called J, and it's too scary for this lecture. Instead, you should read Egbert's book and find where he describes identity types and what this J is doing. So, reading material. Why am I doing this? Because if I wrote down the J now, first of all, I would make a mistake. Then, after I fix the mistake, I would try to explain this to you. Then it would be 11 a.m. and you still wouldn't really get much from it. This is really something that we don't want to look at, but we can say, what should it be? Okay? What should how does one use the fact that two things are equal? So, okay, well, informally speaking, what are some basic properties of equality? First of all, it's an equivalence relation. It's reflexive, symmetric, and transitive. But the actual really essential bit of what equality is called the substitution rule. It says if A equals B, then you can replace A with B, right? That's what it is. So that's what we should capture. Now, there is a fancy way of capturing that idea, which is if you say that equality is the smallest equivalence relation, it turns out you will capture that idea. So what this rule J says is equality is the identity type is the smallest reflexive relation on A. If you think about it, take a set A, consider all equivalence relations. Which one is the smallest one? Equality, right? So that's what the rule will say. I'm not going to show you the rule, but that's what the rule says. There is a complication. The complication is that you have to make things sufficiently dependent. And that's the complication that you will read about. But keep this idea in mind, that we're just trying to say that equality is the least equivalence relation. How does that help? Well, it turns out that helps in establishing all sorts of properties. From the fact that equality is the least equivalence relation, you can show that it is reflexive, you can show that it is symmetric, you can show that it is transitive. That all follows from that fact. So it's quite an ingenious construction by Martin Löf, and so I highly recommend that you read it. You will not see this J directly in Lean, because nobody ever uses it in its pure form. What you see is derivatives of it. And we will see those, definitely we will see those. And maybe on a rare occasion, we will have to actually look under the hood and maybe discuss this J business. But for now, we don't have to do it. Okay, let's also discuss what happens here. We have this identity type, but then we said we had equations. So now it seems like we have two kinds of equality, because we have equality as a judgment where the thing we wrote the last time, the two terms are equal. Now we suddenly have another thing. So how do they relate? Okay. Also, here's another thing that you should be wondering about. The way I wrote this naive attempt here, okay, so these are the rules. The way I wrote this naive attempt up here, it was definitely saying, one day I'm going to discover how this thing gets turned on. Here I have x and y, and here I have then refl ax is an element of this id a x y, And it doesn't matter if I stick in X or Y because they're presumed equal anyway. So, but here I only have A. This is kind of weird. Here I have AA, right? So I would actually imagine that I should be able to get A comma B when they're equal. Well, yes. So actually what we do have if A equals B at type A, so if you have A and B and they're both of type A, and they are equal in the sense of equality that we had the last time, where you just write it down as rules, then actually REFL A of A will have type id AAB. This is what is going to happen. Why? Because one of the important rules, I did not spell out the rules for equality the last time, but if we wrote them down, we would write down 4 rules. We would say it's reflexive, it's symmetric, it's transitive, and we would have a very important rule, the substitution rule, which would say if you prove that 2 things are equal, you can replace one with the other anywhere you like. So what you do is you say, aha, okay, by this rule up here, REFL AA has type REFL AA, it has type id A AA, and because I know that A equals B, therefore I can replace any one of these A's, the little A's, any one I want, I can replace it with B. So I could replace just the first one or just the second one, but this is what I'm trying to do. So by the rule of substitution of equals, these are equal, I can then replace. Yes? Question?
So we need to keep track of all the possible terms in this identity type to be then able to make these substitutions.
This kind of substitution you can just make, because this is judgmental equality. The kind you're asking about is this J business, which I skipped. There, of course, you have to know this deconstructor. So how do deconstructors work? How does a projection work? The way a projection from a pair, if I have an ordered pair, I can project out the first element. When I'm projecting out the first element, do I need to know what the pair is? Yes, of course. I need to have the pair in order to project out the first element. So I can translate now your question to this J. When we use J, does it have to know which element of the identity type it got? You might naively say, no, because REFL is the only possibility. We don't have to know. No. REFL is not the only possibility. It could be a variable, for instance. And you say, but this variable, its possible value is only REFL. No, it's different. When it's a variable, it's not the same as knowing that it's actually REFL. How do you know? Why? Well, because somebody might have assumed something crazy, like 0 equals 1, and then I will be able to produce lots of different elements, right, when I shouldn't be. I might be working under some hypothesis, such as there is an element of it that isn't REFL. So in general, rules have to be general. In general, yes, J will have to know which element of id, which identification. By the way, the elements of id are called identifications. That's why it's called an identity type, and its elements are called identifications. So if I have an element of id A B, I call it an identification of A and B. So yes, you will have to know which path. And homotopy type theory makes a science out of this. Yes. We don't want that science. We are going to ask something else. We are going to ask a much more naive question. So we see that if our type theory can prove the judgment that A equals B, then REFL A can be used as an element of the corresponding type. But maybe we could have this. If I have an element of the identity type, let's call it P for path. If I have if I have an element of this, can I maybe then say, well, but then it should be the case that A equals B. Did I write subscript 8 last time around here or something? Maybe I wrote this. Who knows? To be a little bit more precise. Can we also have that? Well, this thing has a name. It's called the reflection rule. It's called equality reflection. This is a gift from hell. A gift from hell is going to be, it's going to look really, really good, and you really, really want it because it would be nice, right? Because this is what we're trying to capture. We're trying to have a type that corresponds to equality. So the first rule is half of this correspondence. If I have equality at the level of judgments, then I get an element, then I get an identification. But if I have an identification, then presumably I should also have the corresponding equality. The rule has a long history. I think it was probably in the early versions of Martin Love's type theory. It was present there. I spent several years thinking about how you might implement a proof assistant that has this rule, and the answer is with difficulty. So this rule turns out to break lots of algorithms that proof assistants use because it makes equality, this relation equality at the level of terms, it makes it undecidable. The reason for that is that once you have a very expressive type theory, you can construct here a P. So this A and B, you can arrange things so that in order to construct P, you have to know something like, you have to have some evidence that you will never know whether you can find it with an algorithm, such as a machine will stop or something like that, right? So your algorithm gets tangled up in general questions of computability theory, and you don't want to go there. You lose your algorithm. You can still make an algorithm that will exhaustively search for all possibilities, and if it finds one, it will say, yep, they're equal, right? Because you ask your algorithm, is A equal to B? What does the algorithm have to do? It has to find a P. How will it find a P? Well, that can be very, very complicated in general, but it can still try to enumerate all possibilities. If it finds one, okay, then it's done. But it will never know whether it will find one. So if there isn't one, it'll just search forever. So you would end up with an algorithm, first of all, which is extremely inefficient, really, really inefficient. And then it would just run forever instead of saying, no, these are not equal. So that's not good. So in general, this rule is not unreasonable from a mathematical point of view. It kills homotopy type theory. So now, depending on which side of homotopy type theory you stand, you might consider this to be reasonable or unreasonable. It gives you this, it's very close to this view that types are sets, but it's not algorithmically feasible. So proof assistants do not include this rule. We will not have it. What will be a consequence of this? A consequence of this will be that we will very often have to explain to our proof assistant why things are equal. It will not know. Sometimes it will not know because its algorithm is not perfect. It's still pretty good, but it's not perfect. So there will be times when you have to explain. So for instance, something like commutativity of addition of natural numbers, you will have the way it's defined. You define plus using recursion, and then you say, is it commutative? That will be a proof by induction. You prove by induction that addition is commutative. Okay, any questions at this point? So if not, then the next thing we want to address is universes. The idea of a universe came up as soon as people started thinking about sets and classes, because somebody said, how about the set of all sets? It's a very, very convenient thing to have a set of all sets. That's really nice. Unfortunately, it's also inconsistent. So it's too nice. It's another gift from hell. So something needs to be done about it. But why do we want to think about this in type theory? We want to think about this in type theory. There are good reasons why we want this, because so far we really have you see, we have sort of everything is duplicated at the level of types and the level of terms. We have the level of types, where we speak about types, and we have things like A is a type and A equals B. And then we have the level of elements. Stupid machine. At the level of elements, we have similar judgments. A is an element of A, and A and B are equal. And you see that there is a kind of duplication going on. So a little bit, right? So if you're going to implement a proof assistant, you are thinking, oh my God, I will implement substitution twice, and I will implement type checking twice, and I will implement parsing twice, and my grammar will be twice as large. Everything will be duplicated. So from a practical point of view, this is a bit nasty. But it's also quite natural to say, but you know, we are formalizing a theory of constructions, but some of the constructions are types. We also construct types. After all, these things here, they're just constructions of types. Well, didn't we say that we described constructions using types? Yes, we did. Well, but then there should be a type that describes constructions on types, and that would be a type of types. So in a universe in general, the idea of a universe, this is a type whose elements are types. Perhaps not all types, just some. There could be special types. Or maybe, you have a kind of dumb universe that has 7 types. That's not going to be very useful, but you could have one. So that's the idea. And we want to see how far we can bring it. So here's one that does not work. If we try to say that you have a type, which is the type of all types, including type itself, then you get Martin-Löf's first version of type theory, okay? But this is paradoxical. In what sense is it paradoxical? This is Girard. So this is how Girard, I think this is essentially how Girard came onto the scene. Like, he showed up and he said paradox in Martin-Löf type theory. In what sense is it paradoxical? It's paradoxical in the sense that if you have a type which contains itself, then you can show that every type has an element. But if every type has an element, then the type of identifications in natural numbers of 0 and 1 has an element. And you should be unhappy about that, right? Because your type theory now proves that there is something in 0 that there's an identification from 0 to 1. So I think it's fair to call that a paradoxical theory. I should, however, point out that for the purposes of programming, where you just write source code, you don't read types as logical statements. They are just constructions. They're just data. You couldn't care less whether there is some data. I mean, it's good to have data, right? So for the purposes of programming, it is actually quite acceptable to have type in type. So type theories that have a type of all types that contains itself are also a thing. They're just not used for foundations of mathematics because they can't be. They're used for programming, and you can do lots of crazy programming once you have this kind of freedom. Okay. So if we can't have this type in type, so let's underline this. Let's make sure nobody thinks that this is okay. Okay. So I need to do something like here. Okay. Then you say, what can we do? Well, but Russell already studied this question, right? So first of all, he was the first to point one that you can't have type in type, can't have the set of all sets. But also, he then proposed a solution, which was Russell's type theory. Well, what did Russell's type theory do? What it did was it built a kind of a hierarchy, which is to say you can't have a type that contains them all, but you can have a type universe that contains so-called small types, but itself is large. But then after that, you can make these large types, and there's another universe that contains the large types, but its size is super big. And then you make super large types. And then there's going to be another universe of super large types, and so on. Now, that's what you can do. Set theorists said, no, thank you. And they just had two levels. Okay. So the two levels are called set and class. Yes. So these are small and these are large. And this separation then is okay. So how would we use this idea in a proof assistant? In a proof assistant, we would say, oh, okay, it's not that difficult. So we're going to have a type. By the way, once you have these classes, one of the classes is called V, usually in set theory, and it's the class of all sets. Class of all sets. Why is it called V? Is that a German thing? Okay, but von Neumann but I mean, did he call?
I thought it was the shape of the cumulative hierarchy.
Okay, homework. Why is the class of all sets called V? So, well, if we just simulate this, we're going to say there is a type. Let's call it type 0, okay, to distinguish it from this, which would be the type of all. So we think of SMETs as, so we would say something like small types. This would work. This happens. For instance, this happens in Haskell, where it's called kinds. Okay, you have in Haskell, this thing is called star. Another homework, who is to blame for this ridiculous thing that you call V star? Okay, so there was a conversation we had, when was it? Yesterday with pizza, or I don't know, this last week, but I would like to know who it is to blame. I know the French are propagating it, but maybe somebody else invented it. Okay, so they also use box for type 0. Anyway, strange things happen. Now, this is a good idea that will work, but for our purposes, it's not going to be sufficient. Suppose you have a proof assistant where you say this. What kind of trouble will you get in? You will get into the exactly same kind of trouble that Grothendieck got when he started category theory. What was Grothendieck's problem? If you use sets and classes, and then you define the category of groups, it is going to form a class because it's going to be large. But then you will say, how about the category of all categories? And now you have a problem. Do you mean the category of all small categories? The ones that live in sets? You can do that. But you can't have the category, literally the category of all categories, because it's too large. It's super large, but there is no next level after class, so you can't have it. And Grothendieck had a solution. He said, well, I just want to have more. Okay, and so we're going to say, yes, you can have more. And the reason you want to have more is because you don't want to stop. Whatever level you stop at, that's the level at which the mathematician is going to come to you and say, this is stupid. I want to write down a theorem, and the system doesn't allow me to write down the theorem because it says that there is no universe of this size. Give me the universe. Okay, so we're going to give them the universe. This is a very dangerous game to play with mathematicians because it's very unlikely that we will give them sufficiently many universes. But let's give them enough so they don't notice, like, say, for one graduate course in formalization. Okay, so the idea is that we have to keep going. We want to keep going. So keep going. Just like Grothendieck, except a little less than what he said. Okay, we're going to be a little bit more conservative. So we're going to have type 0, which is sort of the first level universe, which contains small things. So this one contains things like, there are going to be things like natural numbers and booleans. These things will be in type 0. But then there will be type 1. And type 1 will contain things like type 0 or functions from type 0 to type 0. That will also be in type 1. So lots of things. But then we will have type 2. And we can just keep going. So in general, we will have a hierarchy. Type indexed by alpha. And now the question is, what is this alpha? And the answer is, it's a level. And then you're going to ask, what is a level? Well, that's an interesting question. It looks like it could be natural numbers, but it cannot be precisely natural numbers, because if it were, I could show that there is a type. I would make the product of all these levels indexed by natural numbers and ask, where is this type? So this would be when the mathematician has discovered that we tricked him, and then he would want to have a type of level omega. And then maybe we give him omega, Agda does. And then he would make omega plus 1 and omega plus 2. Of course, Agda goes up to omega plus omega, then it gives up, right? Do we know any mathematicians who want more? I think maybe Egbert used them all up when he predicatively defined locales. So, and then they told him not to do that, the developers. So we need to do something about these levels. For us, it's just going to be numbers, but it's a type that is kind of a little bit special, and we need to worry about it, and it's separate from natural numbers. So it's got natural numbers, but it doesn't have induction and recursion. So that prevents you from defining certain things. Why is this idea useful? Well, it's useful because now, well, it's a high price we paid, right? We wanted to get rid of half of the things to have just this. We do, because now we can always replace A is a type with A is in some universe, because every type that we have is going to be in some universe. So that's nice. So we can implement just half of this stuff, but we have all these universes. So there will have to come back later on. We will have to come back to the question of, isn't this a little bit impractical? What are some practical ways of doing this? For instance, I can now define the category of all categories, or the category of all groups. I can define the type of all groups at every level. So every level has its own version of groups. So if I want to prove a theorem about groups, will I have to pick a level and then I prove a theorem about groups at level 3? And then if I have a group at level 4, then I have to reprove the theorem at that level? That seems dumb. This is precisely what worried Russell with his stratification. It's the same problem. Namely, the problem is, it's a fine idea, but who is going to work like that? And we will have an answer. Proof assistants make this stuff a lot more convenient and easy, so that most of the time you don't worry about the level. You just do everything irrespective of what level you're at. It's called universe polymorphism. Okay? So we have the idea of universes before the break. Allow me to introduce just one more universe. Prop. So this is a very small universe, seemingly, because it would be the universe of logical propositions. So this would be something like the universe of sub-singleton types. So the universe of logical statements. Now, you should raise your hand and say, don't we have some sub-singletons at level 0, and we have sub-singletons at level 1, and then we have sub-singletons at level 2? Yes. So really, it should be prop sub alpha, and say the universe of sub-singleton types at level alpha, and homotopy type theory does this. Because we are doing set theory, we're not going to do this. We're going to do something a lot simpler. We're just going to say, no. Actually, we have a prop which is sort of special. It's not derived as sub-singleton types. We're going to say this is a primitive notion of propositions, so a universe of propositions. And we will then have rules about what this universe is doing. And we will see when we start formalizing things, we will see how it works. I'm just saying there will be one like this. How do you imagine these things? Okay, so you imagine type 0 as classes. Class. This is the class of all sets. Type 1 is the superclass of all classes. Type 2 is the superclass of all superclasses, and so on. Prop, in set theory, with excluded middle, you can show that this prop business is actually isomorphic to just having a set with 2 elements. But without excluded middle, you can't show this. Okay? So without excluded middle, it's something weird because it's small. You can show that there aren't 3 elements in it. There are not 3 distinct elements in this prop. But you can't show that it's only 2. Okay? So I will try to avoid this intuitionistic stuff. I'm just explaining at this point. There will be a universe of propositions. If you naively, you can just say this thing contains true and false. But you will see when we formalize and use it that it's not just true and false. It's much more expressive than that. You don't. Why? Because it's only true and false up to logical equivalence. But logical equivalence destroys meaning. Here, I will tell you a famous theorem up to logical equivalence. True. Okay? It's clear that it destroys meaning. Maybe it was Pythagoras, maybe it was, maybe it was Fermat's theorem, who knows what it was. So prop does not actually quotient by equivalence, so it makes these distinctions, right? So you can actually write logical statements, thank God, because it would be super strange if our proof assistant only allowed us to write true and false. We could not express any theorems that way. Okay. A break for 15 minutes, so come back at 25 past.
Apparently V comes from verum, by Peano.
Peano, Peano for verum.
Yeah. Truth? Yeah, Latin for truth.
Cool.
And then von Neumann didn't use. No, it's fine.
Okay. If I asked you right now, can you make any types at all? You'd have a problem because we only have constructions. We don't actually have any base types. Well, you have a universe, let's say. So right now, what we described was a bunch of constructions that assume that you have some types and then they make more types. and we have universes. That's not very cool. So let's have at least one decent type, the natural numbers. We're later going to return to the more general idea of inductive types, of which the natural numbers are an example, and proof assistants, almost without exception, at least Koch, Agda, Lean, they support construction of general inductive types, and then the natural numbers are just one example of that. But it's good to maybe look at something familiar. So let's look at how one would introduce natural numbers into type theory. The pattern that we're going to see here can be generalized and used for many, many other things. Okay, so let's go with this. So as always, you would say, well, if we're introducing a new kind of construction, there should be a corresponding type, in which case, in this case, it's not a construction, it's just a type. So our first rule would just be that the natural numbers are a type. Let's practice universes. So we would say we have an n and it's at type, let's put it at the lowest level, type 0. In principle, you could put it in anywhere you want it, but let's not be that crazy. Okay, now we have a type. Next step, we have to explain how to make its elements. How do you make the elements of type MAT, natural numbers? Well, you would say there is a constant called 0. I here used the actual numeral 0. When you get to practical matters, this becomes horribly complicated because mathematicians want to use this symbol for all kinds of things. Not just the zero natural number, but also 0 the integer, which is not the same thing, but also 0 the rational, 0 the real, 0 the complex number, 0 as an element of a ring, the 0 matrix. So they want to use 0 for 20 different purposes. In fact, they want to use 42 for 20 different purposes, because you would interpret 42 either as a natural number, an integer, a rational. I can always do this, right? Whenever I have a numeral like that. But then they will also want to say, well, but you can interpret 42 in any field actually, or in any unital ring, because it's 1 plus 1 plus 1 plus 1, 42 times. So there's something going on there that we need to address at some point, but right now we are just being very formalistic. Okay, so then there's going to be one other construction, which is the successor, which in type theory you would write it like this. You would say, if I have an element, let's call it E, an element of n, then I can make a new element, let's call it successor like this, E of n. Okay, so now I know how to make elements. If I stop here, I don't have natural numbers. If I stop here, I have a type. I know it's got a bunch of things in it, 0 and successor of 0 and successor of 0. But for instance, I don't even know whether they're different. And I certainly can't prove much because I don't have an induction principle. I need an induction principle. Now here, something interesting happens. Here we're going to see for the first time how a benefit of starting with type theory and having logic as a special case. Because actually what we want is not just induction. The induction principle is a principle of logic that allows you to prove logical statements about natural numbers. But you also need recursion that allows you to define things by recursion on natural numbers, like, well, a recursively given sequence of reals. Or there are many recursive constructions in mathematics where you do something by recursion on natural numbers. So, do we need two principles? Do we need a principle of recursion and the principle of induction? It seems that way, but in fact, no, because everything is types, we just need a single one, and then we can specialize to other cases. So how does this work? Okay, so this is important now. Okay, so pay attention, because I could just write it down, but I'm going to try to explain why it has to be the way it has to be. Okay, you want to say that I want to say the following. I gave you some ways of constructing elements of n. I would like to naively say these are all the ways of constructing the elements of n. However, it is extremely difficult to say this in a naive way, because what am I going to say? How do I say these are all of them? Well, they're not literally all of them, because, for instance, later on, I might have some function, I apply a function to something, blah, 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 I get a natural number. So who knows? What I really want to say is n is generated by 0 and successor. So now we have to think algebra. Okay. If in algebra you want to define a homomorphism from some structure, say, let's take a concrete example. Suppose I have a group G, a group, and I know that it's generated by 3 elements. Let's call them A, B, and C. And now I want to give you a homomorphism from G to H. Do I have to define what this homomorphism does on all elements of G? No, I only have to specify what it does on the generators, because every other element of G is a combination of A, B, C. And so I will know that once I know what phi does with A, B, and C, phi is determined, all of it, uniquely. So I just need phi of A, phi of B, and phi of C. And this is, in fact, the universal property of being generated. This is what it means to be generated. When people say that a group G is generated by generators A, B, and C, they might say this means, I just said it, right? I said every element of G is a combination of A, B, and C. Well, what do I mean? Okay, for every element of A, there is a list of A, B, C, and A inverse, B inverse, and C inverse, such that if I multiply that list, okay, so it's something complicated. There is a much better way of saying what it means for G to be generated by ABC. What is it? It's the universal property. It's the category theory tells you how you should say it. Because that's equations. That's still algebra. I don't want any of this nonsense. There exists a finite list, la la la. That's not algebra. Algebra is operations and equations, or if you wish, diagrams. All right. So let's write this more diagrammatically. Diagrammatically, this says I have a set of generators. There is an inclusion of these generators into G. If I have a map here into H, which maps generators, so some map F, then there exists a unique map here called F bar. Okay, that's the universal property of being generated. So this is free generation, to be quite okay. So freely, let's be careful. Freely generated. If it's just generated, there could be some further equations that hold between A, B, and C, in which case this F would have to respect them. But I don't want to get into that. So I'm going to say, let's think about what it means for a group to be freely generated by ABC. Okay, it means literally this. There is an inclusion of the generators into the group such that for every map F that maps the generators, that already uniquely determines a homomorphisms on all of G. That is the correct way of saying what freely generated means. That should be the definition. For many, many reasons, that should be the definition. It's not pedagogically correct to teach free groups this way, although one would be tempted to do so, because then maybe one would create students whose native language is category theory, and that would be a lot of fun. For instance, we made some students whose native language is homotopy type theory, and that's a lot of fun. Okay, so freely generated. There we go. Okay, so now the idea is the same. This is still algebra, so we should be able to do it. Okay, so what are we going to do? This passage from f to f prime, that's an operation. Bar is the operation that we want. It's this bar that we want. Because that tells us how to use G, how to make maps going out of G. It has to be the same procedure. It has to say, if you know what a function does on the generators, or right, then you know what the function does. There is nothing else. Okay, so let's see. There's a complication because it's not quite the same. We obviously have one generator for the natural numbers, which is 0, but the other thing is not a generator. It's some sort of a generating constructor. Successor is not a single element. It's a generating constructor. But following the same idea, we will still try to say the same thing. So it has to be about functions going out of natural numbers. First of all, just like homomorphism, to describe what it means for a group G to be freely generated is to say, to explain how to make homomorphisms from G, as opposed to G, but from G, okay? So that's what we want. So what we want, something that explains how to make maps out of natural numbers. Complication number 1, we don't have like simple generators, we have a generating construction successor. Complication number 2, we want to do this with the dependent types. So everything is going to be dependent. So that would be like not having a single group here, but having a family of groups depending on G. So it's going to be more complicated. Now we do it, okay? So now I'm going to say what it means. I want to have, so suppose, okay, so now first I'll need this H here that I map into, but it's not going to be a fixed type. It will be parameterized by natural numbers. So I'm going to say, suppose I have some family A of types. And now I can freely use universes. And I should now write type sub alpha. And then this will get quickly annoying because I will have to write type sub alpha, type sub alpha, type sub alpha. I will just use type and imagine that I have invisible ink with alpha, because this is precisely how we're going to work with proof assistants. In many respects, the proof assistant can take care of the levels. So we don't want to think about levels. They detract from mathematical meaning. So we don't want to do that. Okay, so alpha, I go, so I have a type family. That's the role of this H here, okay? Then I want to say, I know what to do with the generators, okay? So to say I know what to do with the generators, I have to say, oh, here it would be, I have an element that corresponds to f of a. So now I need an element that corresponds to 0. So I have an element, let's call it B for base case, which is in A of 0. So now, you know, things are getting dependently typed. So that's why I have A of 0. And then now I need to do something with this business here. What do I do with this business here? Well, successor has to work like this. I have to say, oh, okay, given any natural number x, and suppose I have an element y in A of x, I can create some new element, let's call it I for induction step, which may depend on the x and the y. And it creates something in A of successor of x. So this is how I now say that successor, I know what to do with successors, because a successor wants a previous step to make a new step. Then also when I'm thinking about what to do with the generators, I have to pass from the previous step to the next step. So now if I have these things, then, well, then I should be able to get a function from natural numbers, right, out. So what I will get is okay, I will get, let me be a little, okay, I know some of you will hate me for this, but this is what you should do now. Move this line a little further down, okay? I will not explain what function I get. I will explain how to map an arbitrary element of G. So now I say, suppose you give me any natural number, let's call it E. I will now explain to you how to make an element of A of E, because that corresponds to giving you a way of constructing this F bar. For arbitrary element of G, I know what to do. For an arbitrary natural number, where I don't know whether this E, I know secretly that this is just some successor of 0, but it might also be a variable, or maybe I have funny assumptions that say that there is a strange number. So anyhow, I have a general E, and I will need to explain what this is. And this is just essentially, that would be like, oh, I have an E in here. Well, what do I get here? I get F bar of E. Okay, so I want to say that. So then I get something. Okay, so the something I will call ind for induction on natural numbers, because there could be other induction principles running around. And this is an induction on the family A. And here is my base case. And here is my induction step. And here is what I'm doing. Bye-bye. Okay? I just collect all the data, because this is what destructors do. Like when we had the case statement, or we had the projection, right? We had the projection, just a pi 2 of whatever you have. So you just invent a name, which is ind, and then you just list all the stuff. Okay? Equations. Well, yes, there are some equations. You are going to tell me the equations. What happens if I say here for E, I say, what element will I get if I apply this to 0? What do you expect? B. I should, at 0, I should get the base case. And what do you think I should get if I apply this at a successor of some element, let's call it E? What should happen? I should make a recursive call, right? How do I make a recursive call? Okay, so I would make the recursive call. It would give me a result, and then I will use this, because this is how I make recursive calls. This is the induction step, right? So it's going to be I applied to whatever number I am at. So I have to tell it what number I'm at. I'm at this number, right? I gets me to successor of E, you see? I want to get to successor of E using I. How do I do that? I say I applied to, what do I plug in for X? Well, I have to plug in E so that I get successor of E. Okay, and then I need to give it Y. Y is something at the previous level. How do I get something at the previous level? I use a recursive call. And now there are two ways of reading this principle. One is what I just did. I read it as a recursive definition. This is how you give recursive definitions. You say, we have a base case and we have an induction step. We have a recursive step where we, in order to get to the next step, we look at what we got at the previous one and then we do something with it. The I will do something with the previous step. But this is also read as the induction principle. If you think of A as a logical statement, so instead of N, this could be actually any universe here. So if we mapped into prop, then A would be a logical statement about natural numbers, and this would literally be induction. It literally is induction. Okay? There's another way to write this, which I think is how Egbert does it in his book. which some of you may find more pleasing, but for formal purposes, this is more basic, but I'm not going to get into that. So another way to write this would be to write down what int is. You would say int n is something that. Okay, let's write it down as a function. Int takes a bunch of arguments. What arguments does it take? It takes, first, it takes a family of types. Then it takes an element b. Sorry, I don't have to name this one, right? So, okay. So it takes a family like this. Then it takes a base case. And it takes the induction step. So let's write what the induction step does. It takes something which, given any x in natural numbers, takes you from a of x to a of successor of x. Okay, so I start with a family, I have my base case, I have a way of making an induction step. Then I don't want to break the line, so I'll do this. Then for every natural number e, maybe let's call it y. Y, natural number, I get something in a of y. So let's read again. This is called the motive of my induction. This is called the base case. This is called the induction step, or also recursion step. And this, what is this? Well, this is a section. Why do I say a section of A? Well, because this is like a function which for every natural number y gives me something in A of y. So the geometric picture of this is that I have a, let me draw the geometric picture. The geometric picture is this. Here you have natural numbers. And then at 0, I have here, oops, A of 0. At 1, I have here a of 1, and so on. And at y, I have here a of y. And what this thing does is, where are colors? Colors are gone. Help. Okay, I give up. No colors for you today. Where did colors go? They updated this thing. Ooh, colors. Okay, so our section, what does it do? You pick, so what will we get at the end? Here, we're going to get the base case, right? That's going to be our B. And then here, we're going to get whatever we get. And then here, we're going to get whatever we get. So we will get a bunch of these elements, one in each of these balloons. So if you think of this as a space that maps down onto the natural numbers, then what you see above 1 is called a fiber at 1. Okay? So we're doing topology now, by the way, and geometry. So what do you call a map that goes in the opposite direction, which assigns to each element in the base something in its fiber? That's a section. That's what it is, right? So those of you who had logic and sets with me, now you finally understand why I teach the words retract and section in the first year, okay? Because I want you to start early. So that's what it is. It's a section. Okay? This is a general principle. We have a type, and we're describing what sections over it look like. And if you go back now to other rules like products and sums, you will see we did the same thing. Those rules can be read as describing what does it take to have a section of a family indexed by our type construction. So it's always about maps out of my type, just like the universal properties of free objects in algebra. Free objects in algebra are described by morphisms out. And this is a morphism out of M. Except because things are dependent, it's a section, it's not just a map. It's a dependent map. That's enough in the first iteration about natural numbers. I will just say that this generalizes to various other examples, but we will come back to them. I want to spend the last 10 minutes talking about, if I manage to scroll, yes, I managed to scroll, invisible mathematics. On the one hand, we have formalisms that we use to that as logicians we imagine these are the formalisms that describe what mathematics, how mathematics speaks, how mathematics operates, such as logic, set theory, type theory. They're very precise syntactically, they have rules, you're supposed to follow the rules. And then it is a generally accepted fact that if we wanted to, we could use these to formalize, to do everything that we do as humans, and we could do this. And people tried in several important cases. One of the early ones that I was told about when I was a student was the formalization in the automath prover. Somebody formalized the book about complex numbers. The book was by, okay, it's a German book. It'll come to me. But somebody formalized a thick book about basic properties of numbers. The thick book was thick because it had very detailed proofs. And when I was a student, that was the evidence given to me by my professors why formalization is totally boring, irrelevant, and nobody should ever do it. Somebody tried to formalize a book. Yep, you can do it. Now we can go on as business as usual. Well, unfortunately, computers came along. So people got interested in formalization for various reasons. First, it was the computer scientists because they wanted to prove their source code correct, and they were facing tens of thousands of extremely boring, simple theorems that they didn't want to do by hand. That's a good use case for computers. So maybe you don't want to formalize geometric topology as a professor, but certainly you don't want to manually verify 10,000 theorems about if-then-else statements and array indexing. So computer scientists started to do it, and they never stopped. And now it's at the door of mathematics. Now you could argue that formalized mathematics is our last stand before the AI overlords, because this is the only tool that I see that can protect mathematics from AI. What are you going to do with AI that submits papers to archive.org? Nothing. You just lose, right? You will never know whether it's correct. You have stand no chance of verifying whatever the thing is doing. So you have to fight machines with machines. And the machines that are going to fight our battle against AI are proof assistants and proof checkers. But for proof checkers to work, they need to use formalized math. So now we have a reason to use formalized math. Also, we want to formalize all the math so that our AI overlords can learn all the math. We want them to learn not from the archive, because God knows what they will do. We want them to learn from formalized math, to produce formalized math, because then we can keep them in check. So, two reasons for formalizing math. One, to fight against the AI overlords. Two, to make the AI overlords. Okay? Two very good reasons. Which brings us to an important point. So long as we don't have machines that just, you think vaguely about some math and then the machine tells you how you would actually do it, for the foreseeable future, we will have to formalize math using these tools called proof assistants, where you have to do things kind of manually still. So you want the tools to conform to the way that humans do mathematics as much as possible. If we're going to implement these formal systems in proof assistants, it becomes crucial to ask, will we really be able to do so? Well, somebody once formalized a book in the automat system, which was very, very primitive by today's standards, but also revolutionary. And they succeeded. However, I would not recommend formalizing things with automat. So we need to think carefully about what mathematicians actually do. And let me just, there is a talk I gave about this, and I'm posting links and references on the lecture notes, and you can find resources in the course materials. I gave a talk that I'm rather proud of about this, where I explain why this is important and what goes on. But the main point is this. No, it is not true that it is easy to translate human mathematics to formal mathematics. This is false. However, it can be done. It took several decades of research by computer scientists to get to where we are at the moment. At the moment, we seem to be good enough to at least entice large groups of mathematicians to spend unreasonable amounts of time to formalize mathematics for the benefit of our future AI overlords. What needed to be done? Well, what needed to be done was we had to figure out what are the parts of human mathematics that are there but are not visible, that you need to understand. So I will just demonstrate this because we don't have a lot of time. And then I invite you to look at the slides, which they have speaker notes. So it's like a lecture, or, the video, you put it like on 2.5 speed, and then it's very funny, and then look at the video. It's not too long. So the statement that I use is this. If f from x to y is linear, then f of 2x plus y equals 2 times f of x plus f of y. I claim, because this is a graduate course with smart master students, I claim you understand what I said. Okay, this piece of communication is completely acceptable between two mathematicians. Okay, there might be some questions lurking on, but more or less you understand what it is. The reason I claim you understand is because you also can tell me how to prove it, right? You say because f is linear, we can rewrite f of 2x plus y as f of 2x plus f of y, and then we can take the 2 out. You can say these things, okay. But if we are quite careful, this is not formal enough, okay? So let's just try to list the things that are missing. What else should we be saying? So what are the things that are missing? So the first thing that's missing is that presumably x and y are vector spaces. So we never introduced x and y. What are they? And you just simply guessed that. So what is the guesswork that your brain did? When you read this, what does it guess? It guesses that these are probably vector spaces. But over what? Well, over a field K. So suddenly we now have another object that is not even mentioned. What else did you have to guess?
X and Y arbitrary.
Yes. Where X and Y range over. So X ranges over what? The little x.
Big X.
Yes. And then Y ranges over what? Nope, not big Y. It's a trick question.
Absolutely.
Yes. Also over X. So you guessed, right? So without explaining anything at all, you now have agreed with me not only that X ranges over X, but that Y definitely doesn't range over Y. You see, you really do understand the statement. Right? So, okay, anything else?
What 2 is?
Yes. What is this 2?
No.
Well,
And specifically
it could be a natural number, right? I mean, usually it's a natural number, you see. So, but it can't be a natural number. Or maybe it is, but then the dot is something weird. So the fact that let's start writing things down. Okay, let me just put things in where they're missing. So the fact that this 2 is actually, let's try to be precise. Tell me precisely what 2 is, because if we're going to say it's an element of K,
specifically
you have to, I want to know which element of K. So 2 is which element of K? Tell me.
1 plus 1.
Okay, it is not 1 plus 1, because that's still a natural number if I think that 1 and plus are natural numbers. 1 in K plus in K of 1 in K. Okay? How about this one here, this plus? Where does this plus happen?
This plus of X.
This one happens in X. Nobody said that, yet everybody was happy. Where does this plus happen? In Y. Where does this times happen? And where does this times that we didn't even bother to write happen? In X. Anything else anybody would like to say? Where does this equality happen? In Y. Right? Your brain automatically understands all of this. So a proof assistant has to do all of this also. And it has techniques and methods and tools for doing it. And a big chunk of what we're going to do is we're going to learn these techniques. So remember, we will learn things that you already know, but we will give them names, we will discuss them, and we will actually make them explicit. But you already know them. Okay? That's like medicine students in anatomy. They have all the muscles, but they can't name them. They can use all the muscles, but they don't know how it works at the level of nerves. So it's like that. Okay? We will be making many things explicit. So there will be strange things happening in the proof assistant. And I will say implicit arguments, meta variables, coercions, notational scopes. Those are just fancy names for the things that your brain does anyhow. Okay, and we're going to end here. Next time we will actually look at lean. So it would be good that everybody has lean installed, and I will post a little challenge for everybody to test that their lean actually works. It's going to be something on the level of like 2 plus 2. Okay. Yeah. Homework. So homework, keep installing lean. Oh yes, I was going to have a homework. The homework is going to be, apart from installing lean, so I write it here, homework. I will post this also on the course materials or everywhere else. I'm just going to say, find out there's a thing called the natural numbers game. It teaches you lean. Okay? Let's see how far you get. So find it, it's on the net, you work it on it in a browser, it teaches you lean. So entertain yourself with that. Okay. Okay, that's it.